We will start the second lecture of Raffaele.
Okay. Thank you for being back here. Greg, out. Okay. What I decided to do in this second lecture, and we'll see how it will go with this kind of audience, is that we heard a number of times Bill talking about ocean turbulence, microscale turbulence associated possibly with gravity waves. Thierry yesterday was talking about turbulence and associated with wave breaking. Paula mentioned a number of times diffusive processes being small or large, and again thinking about small overturning scales. But so far nobody has told you first how you actually measure that turbulence and whether there is any chance to actually get direct information about the turbulence. And I think the reason why it's important to get a bit deeper in understanding how oceanographers do that is that you get a better appreciation both of what we know about the turbulence and what we don't know, or mostly what cannot really be quantified. And so what we're going to focus for this lecture on, or at least I'll focus on this lecture on, is first to derive a bit what are the principles used to measure the turbulence, so what are the budgets that people try to use to infer what the turbulence is. And then we'll review a number of experiments where this approach has been taken, and we see that there are a number of approaches, so by comparing different approaches we get a bit of a sense of how accurate they are in general. And we'll conclude by showing a couple of experiments where we learn quite a bit about the fundamental properties of turbulence. And here by turbulence I always mean small-scale turbulence and turbulence that mixes across density surfaces, because that's what I'll need in the next lecture to revisit the idea of Stommel and Monk and see, since their work, what have we learned about the ocean turbulence, what it actually, how it actually behaves, and how that will force us to revisit some of those theories. So again, the first thing, we'll go back and for a second recast what I mean by turbulence and diapicnal mixing, and then we'll see that there are three fundamental methods used to measure ocean turbulence. One that relies on the temperature variance budget, which Paul essentially was talking about earlier this morning, so we'll go through that budget a bit again in the context of how you use it to measure turbulence itself. We'll see a method based on turbulent kinetic energy budgets. And finally, we see that there is a completely independent approach that instead relies on releasing a tracer and see how fast it spreads through the water column as a result of the stirring and mixing by gravity wave breaking. And then we review these three experiments that are some of the seminal experiments in the field, mostly because they use all three approaches at the same time. So we're going to have the North Atlantic, an experiment in the North Atlantic that is mostly focusing on the upper ocean, and we'll compare these three approaches and will tell us to what extent they are consistent or not. They're trying to measure the same thing but from very different approaches, and we'll see how they relate to each other. And then the second two experiments, instead we'll start addressing finally the question we are really after is, what are the properties of turbulence through the water column? Are there general principles on how turbulence behave? Where do waves break? And are there places where they're more likely to break and more likely to mix? So this helps me just to explain some of the averaging we do. I'm just showing you from a location in the North Atlantic, but this spectrum will be pretty typical of everywhere you look in the ocean. So this is the magnitude, the spectrum of the kinetic energy, the velocity field. And this is as a function of frequency. And these three plots are from a mooring that had the current meters at three different depths. So you're just seeing the spectrum of velocity at the, well, I don't know, it's a few hundred meters, 200 meters probably, and then going deeper down in the water column. The inertial frequency here, F, is a bit more than 10 to the minus 2 seconds to the minus 1 cycles per hour. It's up here, and the scale moves down. So the inertial frequency is always in the same place because you're looking at the same latitude. But what I want you to notice is that you see that there is a peak. This is generally what is called, well, it's an inertial peak that in this particular location is close to the diurnal tide as well. So you have both contributions. But so you have this peak in energy and this tail. This is generally what we call super inertial energy. It's associated largely with internal gravity waves. Instead, if you look at the subinertial component, you have energy that keeps going up. That is energy associated with balance motion, geostrophic motion. There are motion that evolve on time scale slower than F, and so they have time to go close to geostrophic balance. There is pretty much the same amount of energy in the right-hand side of the base of the spectrum as on the left-hand side if I were able to extract all the way to low frequency variability. So the geostrophic eddy kinetic energy is pretty much as the super inertial one, but there is a big difference in what these two motion. Yep.
If I integrate in my head,
you cannot, because I didn't show you all the way to zero frequency, right? There is much more. I mean, it doesn't
well,
stop
precisely.
at that
So I mean, it's a log scale. So isn't there much more energy in the balance part?
Not really. These peaks are pretty high.
Well, but it's still lower than the maximum.
Well, but the omega is larger, so if you integrate in frequency.
Well, it's a log scale, right? So
we can look at the numbers. The numbers are now not to be terribly different.
Could you summarize what Jacques' objection was about the conclusion?
He was just saying that looking by eye, he wasn't convinced that there is as much energy in the internal wave band versus the subinertial component, but it turns out that the numbers, when you try to put them together, are not terribly different. There might be a bit more in the geostrophic part. In the plot that Bill showed on Monday, he also had the total energy reservoirs. It's, I don't know, is it ettajoules or something, and the numbers are the same order of magnitude. We can try to do it later more carefully. But I think the major issue here is that you don't see the lower frequency, and you would need to integrate the whole component.
What do you mean by subinertial and superinertial motion?
So the inertial frequency is F. So this is, for the upper plot, is where the inertial frequency is going to be around here. Superinertial is all the energy to the right of this plot, and subinertial is everything to the left of this plot. So I'm just saying energy associated with motion that fluctuates faster than F, and energy associated with motions that fluctuate on time scales lower than F.
Can you just say where is the buoyancy frequency in the...
Oh, I don't know. I don't think that it's down here, and I'm not sure that it's measured, because the mooring, the current meter was measured at high frequency, a frequency high enough to get all the way there, I believe. Otherwise, you generally see a flattening of the spectrum. It does change. But it is true that the turbulence, in some sense, it is on scale of n and above. If you really want to see the overturning events, those are very fast. But this is not the instrument to measure them. We'll have to discuss what alternative techniques you need to use to actually see what happens at this very high frequency. You need fast response sensors.
Is there any reason in the lower plot the slope of the balance part even becomes shallower than the...
There is no reason why it should be any value as far as I can tell. So here, he's just fitting it. There is less energy because you're going deeper in the water column. There are fewer modes, but I wouldn't take, I mean, this is the slope in the frequency domain. Arguments are generally given for slopes in the wave number domain. Exactly what that means, I don't know. I don't think there is a universal slope. Everywhere you look seems to be a bit different. That said, we're not going to talk about this subinertia or geostrophic component from now on. So. But there are plenty of publications with plenty of spectra. If somebody wants to dig a bit deeper, understand whether there is anything fundamental about those slopes, might be interesting. So, do I have the other one? This is to make Oliver happy that we are not watching enough movies, so I'll show a movie of a wave breaking. I want just to make the point that the reason why we're emphasizing, or here that we're going to focus a lot on gravity waves and process like that, is consistent with what Thierry was showing yesterday evening, is that these are motions that can generate overturn of density surface and mix across density surfaces. In a second, why is it instead the geostrophic motion on the subinertial component generally cannot overturn density surface, generate mixing? And here, in the argument that we've given on Monday, we are interested in seeing how fast properties are mixed across density surface. That is fundamental to understand how you set the stratification according to Munk argument. So that's the part that we want to focus on. And this is just a simple example of a system that has some shear. So this is a fluid that is stratified. There is light water over dense water. There is a shear. And the Richardson number associated is unstable. So we're going to say that you get some overturning if you let the system go. So it's a spontaneous generation of an instability. These are your Kelvin-Helmholtz roll-ups. But what I want you to notice that first you create all these gradients, and then they get mixed away. So now you generated a new water mass here, which has a density which is intermediate between the other two. So you mix density surface across this interface. This is a numerical simulation, but you can also do laboratory experiments and show the same event. Oh, here I took away that slide. We've seen it on Monday, that the reason why we tend to emphasize gravity waves as a primary process to drive motions of this kind, to try this overturning, is that gravity waves can have very small Richardson numbers that can go unstable to shear instabilities. They can also generate convective instability by generating overturns. And yesterday, Thierry has shown a whole suite of processes that can lead to instabilities of waves that actually break and mix density surfaces. When you go in the geostrophic band, generally the stratification is too strong for geostrophic motions to generate low Richardson number, and so those systems are much more stable, or large-scale motions tend to be mostly a long-density surface and not across. So that's why we focus on how we measure, or how can we measure the turbulence associated with gravity wave breaking, because those are the motion that can mix across density surfaces.
Can I ask a question?
Yeah.
Yeah. Excuse me. In the movie we saw, did we just see the Kelvin-Helmholtz instability?
Yeah.
Is that the same thing than a strong nonlinear breaking internal wave?
Yes and no, right? I mean, it depends how you want to see. Waves are probably more complex than that. There is a time dependence associated with that. It also matters whether there is a true interface or it's a continuous stratified system. So it's an analogy.
So in Kelvin-Helmholtz, you have a shear, to start with.
Oh, I had shear.
Yeah. So that's
well, also
quite
in the
different
gravity
from
waves, I have shear. Actually, it turns out the gravity waves, most of the energy in gravity waves we've seen in the plot before is in the inertial peak. The inertial peak is the peak that has the largest shear. So most of the energy is actually associated with waves that have a very strong shear, and they are pretty horizontal. So in that sense, this is used often as a paradigm. But whether it is an appropriate paradigm, you ask Thierry. Thierry? Well, as long as you have an internal gravity waves, you're going to have shears. So, sorry?
But didn't you impose a large-scale shear independent of the...
Well, assume that this is 10 meters, so large scale is the scale of a wave. So in that sense, the spirit is of a single wave breaking. So I hope I can go through this quickly. At this point, we've seen these equations a number of times. It's just that we are going to use subset mostly of the buoyancy budget that has been introduced, so I don't think we have to do too much. We're going to use the Boussinesq equation. So this is the momentum equation in the Boussinesq approximation. So the density here is a constant density, and the only place where variation of density appears is through the buoyancy force in the vertical momentum equation. We assume that the fluid is incompressible. That's a good approximation for seawater. Then we're going to have equation for temperature and salinity that are just affected by this velocity field, and they are diffuse, and these are really the molecular diffusivity of temperature and salt. So this is the full system, technically. And to keep things simple, because nothing I'll say is really affected by that approximation, we'll assume the buoyancy is just a linear function of temperature and salinity, and it's a linear function through a coefficient that has a gravity, acceleration of gravity, the compressibility coefficient of temperature alpha, and the expansion coefficient for salinity beta. I'll assume they are constant for the moment. It doesn't really matter. We could. Yeah, it will be, but we're not going to talk about viscosity much. The question was whether the viscosity is going to be constant. Yes, we are not going to work on them. Oh, here, well. Yes, it's going to be constant. Variation in viscosity is not something we're going to worry about. So if I have the temperature and the salinity budget, I can just create a buoyancy budget in this form. I just linearly sum these two equations multiplied by appropriate coefficients, so I get a buoyancy budget, except the diffusion of buoyancy is going to involve some funny molecular processes, because the diffusivity of temperature and salinity are actually different. And I just wanted to put it up because I want to explain why we typically ignore the difference in this molecular diffusivity of temperature and salinity, because if you go back now, and this is your full equation for buoyancy, and we take an average of this equation on subinertial time scale. And I want the subinertial time scale because I want to see what is the effect of these superinertial motions, which include waves and wave breaking and all these processes, on the subinertial motion. I think actually that's maybe a moment to pause and understand that there is a big difference I find between what is the questions that earth scientists ask when they're thinking about turbulence versus what the turbulence community really prefers to ask. For earth scientists, typically the question about turbulence is how the turbulence affect large-scale motions. We don't care about the properties of turbulence per se if they don't feedback on large-scale motions. For example, the classical example, isotropic homogeneous turbulence, something in geophysics doesn't have much appeal because if it's homogeneous isotropic, there are no divergences associated with the fluxes generated by the turbulence. Therefore, they cannot affect large-scale motions. And then that's not the kind of thing that we're talking about when we talk about turbulence. So here, a lot of the emphasis will be on turbulent fluxes that affect large-scale motion. That's why I'm taking a subinertial average so that I obtain, as a result, turbulent fluxes at subinertial time scale, and I want to see how they affect the large-scale motions. So this is what I've done here. I take this average, which is a subinertial average, and on the right-hand side, therefore, by doing the classical Reynolds decomposition, I get turbulent fluxes of buoyancy, and there are still these molecular fluxes of the mean temperature and mean salinity. Typically, the turbulent fluxes of buoyancy in the ocean interior, despite the ocean we've been told that it's not terribly turbulent, but it's still turbulent, at least in the sense that these fluxes are much larger than the molecular one, and so typically we ignore them. So at leading order, we are only going to consider the divergence of the turbulence buoyancy fluxes. On top of it, as I said, on subinertial timescale, the vertical gradients are typically much larger than the horizontal gradients, and therefore it's really the vertical divergence of these turbulent fluxes that dominates in that budget. And that's why a lot of the emphasis or a lot of the work that has been done observationally was to see whether we can measure properties of this turbulent flux W prime, B prime.
So what is the meaning then of your bar? I mean, is it a kind of filter you apply? Why do you call
time
it
average?
subinertial?
Let's say subinertia for the moment.
You call it subinertial.
So
what is the
averaging on
relation?
time scale is longer than F.
Okay. But not necessarily infinite. I mean,
But the averaging means that I average of anything that is faster than F.
okay.
Infinite already to the fastest time scale I can. So I average over all of that. So F and lower frequencies, all subinertial motion are captured in this. Maybe most importantly, operation is to make the case. Therefore, all the eddies that this is important because all the eddies that Paula were talking about are in my U bar now because I'm really talking about averages on, say, superinertial time scales that are motion associated with gravity waves and gravity wave breaking on scale of order of 10 meters or so to 100 meters. So it's pretty small.
If you have a geostrophic AD, it will be on U bar.
Absolutely. Because that is mostly mixing a long density surface. That's not the part of the problem I want to address now. So the prime here is very different from what you heard in the previous lecture. That's a problem in every turbulence talk you hear. Everybody uses their own average, but it's always a bar. So how do you go about measuring this turbulent flux, which I think is quite important? You have to realize that it's a very tough problem because we want to measure turbulence in an ocean which is 4,000 meters deep. We heard on Monday from Bill, that the ocean at least is kind to us because tends to generate turbulence or turbulent motions down to scale of order of the Kolmogorov scale, which is close to a centimeter in the ocean. He was saying that's pretty large and I'm happy about that, but still it means that you have to measure fluctuation on this kind of scale down 4 kilometers below a ship that is moving up and down because there are surface gravity waves that have generally a height of a few meters. So it was a challenge. The thing that you might think up front that you want to do, you want to measure the flux of W prime and B prime. Well, then why don't you just measure W and B and then compute the correlation? This is done in convective problems, sometimes in the atmosphere. This is an example where this has been attempted, where by using a towed instrument close to the surface, so at least you avoid the problem of having to tow things 4 meters down. That becomes incredibly difficult, essentially impossible. But this close to the surface, you might think you can do something like that. So I guess this is a plot of temperature along with the towed instrument moving in the water column, and this is a plot instead of W, the vertical velocity. You see that a very irregular signal. These are high passed because we're only looking at, again, superinertial components. We're not going at subinertial components. And then you want to compute the correlation between these two signals and see what comes out. It turns out that the correlation is generally something that's less than 1% of the two signals themselves.
So if you high pass what about the stationarity of the signal?
What about?
I mean,
it's not in here.
Sorry?
it's not in here. These are the fluctuation on superinertial time scales, right? Because I want
Right.
the W prime correlation only on superinertial time
So,
scale.
but if U bar changes, then the statistical property of your prime variable may change too.
Absolutely. But I'll tell you, even if they don't, I stand no chance of actually measuring that correlation because there are a number of other practical issues that come in the story. I had to measure W and B at exactly the same location. That's something I can't really do. They're always going to be spatially separated by scale that are much larger than your Kolmogorov and Bachelor scale. So you already have that problem. You have to assume that that is not relevant. And then you have a platform that is moving up and down because it keeps tilting. So you don't really ever correlate even in the same sense. It's also hard to interpolate one signal over the other and to try to compute that correlation. And the correlation, if you just try to plot it, is extremely intermittent, and you would have to average for a very long time before you get some stationary value. And that's where the problem comes in. You're not likely to be always in the same turbulent patch. At that point, you're averaging over a system that is probably your mean U bar. The mean state is evolving. So as a result, this is an example from Fleury and Dweck that oceanographer tried a few times and essentially gave up because those estimates don't really seem to give you much of useful insight. The reason why you know that they don't is that a gravity wave breaking clearly, as in the example I've shown you before, in a stratified ocean, if it's strongly stratified, will tend to mix buoyancy. So at least it should create a buoyancy flux that is negative because it brings up blobs of dense water and brings down blobs of light water, right? So when W is positive, B is negative, the anomaly of B is negative, so the WB should be negative, and in this kind of estimates, generally you get WB that has positive and negative sign equally likely. So it just turns out not to be an effective way to the calculation, even though intellectually it's probably the most straightforward. So now you have to become a bit more clever and figure out whether you can relate that buoyancy flux to something else you can measure and doesn't require correlation, which is what is really the killer in this approach. So a second approach that was pioneered by Osborne and Cox in the 70s started by saying, what about if you consider the turbulent budget of a tracer, in particular potential temperature? So the first thing is they said, we want to go down that way, assuming that we are in a place where temperature dominates buoyancy. So at least we can probably make some progress. So you start with your temperature budget. Now this is again the molecular diffusivity of temperature. And they say, well, I can write my mean temperature equation by taking out, again, a subinertial average. So this, again, is the mean temperature, advection by the mean of the mean temperature, and then, because you've done a Reynolds decomposition, you have turbulent fluxes of U prime theta prime, the correlation between U and theta, which is what we are after, and then you have diffusion by the mean. I can also write an equation for the perturbation by subtracting this mean equation by the full equation. So that is an equation for the perturbation, right? So that we all understand theta is going to be some mean plus a perturbation. And I'm assuming there are no correlation between theta prime and theta bar. It will turn out not to be the worst of approximation we're going to make. So this is now the temperature perturbation equation. So there are fluctuation of temperature perturbation can be generated by advection by the mean or by the eddies of temperature fluctuations. I can just move temperature fluctuations around. I can generate temperature fluctuation when I have a U prime and eddy that moves the mean gradients because it moves up and down. So now all of a sudden I distorted my background gradient. I generate a temperature fluctuation. This is the term that comes out because I subtracted this equation from that one. So the divergence of the turbulent fluxes appears here. It's a source term. And then I have, again, diffusion of the turbulent fluctuations. This equation is way too hard to do anything with it. But where I can start making progress, I multiply now this temperature theta prime equation by theta prime, and I take an average. So I write the equation for the temperature variance itself, right? 1/2 ddt of temperature variance. Now this equation has, again, the rate of change of temperature variance in the system is given by transport of temperature variance. The motions can transport. If there is a lot of temperature fluctuation in one place, they can be advected in some other part of the domain. There is a diffusion of temperature variance by molecular processes. And then on the right-hand side, I put the terms that will start playing an important role. One is turbulent fluxes acting on the mean gradient. That's, again, if you remember, in the simple movie of a gravity wave breaking, as the instability started, you had turbulent velocities that were moving properties up and down across that interface. All of a sudden, you were generating a lot of gradients. This is the turbulent flux is acting on this background mean gradient, water going from heavy to light. And this generates gradients, meaning it generates variance, it generates turbulent fluctuations. And instead, this is the distraction of variance by molecular processes. If you remember that movie, after a while, after generating all these very large, small-scale gradients, molecular diffusion was entering in and was smoothing and creating this water of an intermediate value. And this is the distraction of variance by this process. So what do you do with that equation? Again, we can't measure all the terms, so we start making some assumptions. The first thing is that I insist that this was a subinertial average. Now we are assuming that it's not just a subinertial average. We are also averaging over a patch of ocean and over some long enough time. Well, let's say subinertia, that is still fine, but we are also averaging over some patch of the ocean. So the first thing we want to assume is that that turbulence is stationary. So we are observing the turbulence might be growing at some time, might be decaying at other times, but we measure it enough times, we have enough realization in that box that we are considering that it's neither growing or decaying in the mean. The second thing we are going to assume is that the turbulence is homogeneous. You see that this is the divergence of term. This is variance that is redistributed between the system. If we're having a large enough box and we assume that this box is not a particular source of turbulence that gets exported elsewhere or a place where turbulence is imported in, but it's as likely to go out or in, the system is homogeneous, and therefore I'm not advecting or injecting variance into that system in particular, so the divergence averages out. Just take a large enough box so that the turbulence is just whatever happens in, meaning the turbulence is generated inside and decays inside without being exported in the net. So in that case, you're left with a balance between the production of variance by, you remember, the stirring motions, the gravity wave breaking, mixing across the density surface, and the distraction of variance by molecular processes. Even at this point, that's not simple enough to be useful, because as we said, we want to measure turbulence from the ocean surface all the way to 4 kilometers, 4,000 meters. The only thing you can do is to have a vertical profiler that moves all the way to the ocean bottom. So you're only going to measure vertical gradients. There is no way you can also measure horizontal gradients, especially because remember that we're going to have to measure gradients all the way down to the scale at which molecular processes act, which is, well, in this particular case, it's going to be a bachelor scale, which, if you remember, yesterday, on Monday, we were told that the Kolmogorov scale is order a centimeter. The bachelor scale for temperature is a factor of 3 smaller than the Kolmogorov scale, because the diffusivity of temperature is smaller than the viscosity. So you're talking about 1/3 of a centimeter. So moving vertically slowly enough, you can probably measure properties of fluctuation on a scales of 1/3 of a centimeter, but horizontally, there is no way 4 kilometers down that you know exactly where you are to measure at the centimeter resolution. So what we assume is that the turbulence is strong enough that it's isotropic. So vertical gradients are equal to horizontal gradients, and therefore the full gradient, graph theta prime squared, just 3 times the vertical gradient. So now I have a system where I have a turbulent flux acting against the gradient, which is balanced by this distraction of variance, and this is the leading order budget. Turns out that indeed, if you are a subinertia time scales, and on top of it, if you're taking average on horizontal scale, the ocean is typically stably stratified. If you are in a region where temperature dominates densities, temperature is also stably stratified, and so the vertical gradients dominate on the total gradients. So this term equal to that term can be recast as W prime theta prime being equal to this molecular diffusivity times the vertical gradient square divided by the vertical temperature stratification. So now it turns out that we'll see in a second that I can measure all these terms. There are ways in which I measure all these terms, because these are all vertical gradients. With a profiler, I can hope to make an estimate of those vertical gradients. Actually, we are going to call this 3 kappa theta ddz of theta prime squared 1/2 chi. It's just the 1/2 is just the convention, and chi is just what is called the thermal variance distraction. The thermal variance in this the distraction of thermal gradients. Yeah.
Can I ask a question, please?
Yeah.
So if it's homogeneous and isotropic, how can U prime theta prime average be non-zero? What would be the direction of this vector, for instance?
Well, what do you mean? Well, think about eventually what happens. You have a W prime theta prime being the dominant term. So I have that every time I move water up, I have a positive W prime, but there is a negative buoyancy flux.
So
the
maybe I
W prime
didn't quite
theta-
get what is isotropic. If it's isotropic, you cannot have any direction that's preferred.
Well, the background state is not isotropic, so W prime is going up and down, but it can create a correlation with theta prime. The fact is homogeneous for the moment, it might mean that on the large scale, or at least on the scale I'm measuring in and measuring at, there is no vertical divergence of the W prime theta prime, but I can have a flux.
Well, no, I guess that's my question. It's
No, but in turbulence you can have fluxes. You might not have flux divergence if it's homogeneous, but why
Well-
shouldn't you have fluxes?
do you get fluxes if everything is homogeneous and isotropic?
Yeah, I mean, they just won't have a divergence, right? I'm giving you the example. I randomly scramble my background vertical gradient, but
Well,
since
if
it's
it's vertical, it's not isotropic.
the background state, well, it could have an infinite scale, right?
Well, that's still not isotropic, is it?
Well, the background state doesn't have to be isotropic. The
Okay.
turbulence is.
So U prime and theta prime have isotropic statistics.
But not the
Well, then
background
how
state.
can the average of U prime theta prime be non-zero?
The
I guess
background state has a gradient, right? So now I'm just saying that I'm looking, there is a big scale separation. So on the scale of the turbulence itself is isotropic and homogeneous, but on much larger scale, there are an isotropy in the system.
Okay, then maybe we should discuss that.
Yeah.
Thank you.
You can have it. You can have homogeneous turbulence on a tracer, which has a large scale background gradient. You're going to get fluxes, right? If I start mixing, I don't need to be non-isotropic to get some flux. That's how I mix coffee and milk every day.
Homogeneous.
But there
It's
is a
not
scale
gonna do
separation, so
squat.
it's homogeneous and isotropic on small scale on the ones I measure on, but then on large scale, think about WKB, there are going to be divergences because it's act on the large scale circulation. So I'm talking about the turbulent patch, and on that scale, I'm assuming it's isotropic.
So what is chi? Is this the definition for chi?
Chi,
Or is
1/2 chi is 3 kappa theta prime z squared averaged. It's just a definition. It's just that we'll see that practically oceanographer can have devised instrument to measure both chi and this background gradient. So you can measure both of them. So you can measure the W prime theta prime. If you remember, then W prime B prime, the buoyancy flux, which is what we are after, is just linearly proportional to W prime theta prime if temperature is the only stratifying component in the place I'm looking at. So the salinity fluctuations are very weak. And this formula is a formula due to Osborne and Cox in 1972. And I'm now showing a modern version of the instrument that they devised at the time. What you have to do is that you need a vertical profiler. This is a vertical profiler. This is the real thing. I think Bill showed, I don't know if it was the same one or not, this is called the high resolution profiler design at Woods-Salt, which is the most accurate instrument of this kind. And you're going to lower it in the water column all the way down to 4,000 meters through the whole water column, and you're going to have thermistors in front of this instrument. They want to be in front because you don't want to have effects of wakes by the instrument itself. They have very fast response transmitter that can respond to very fast time scale, so they can measure very fast fluctuation, and that's what you use to measure your theta prime z square, this term here, and they can measure fluctuation on order of centimeter given the velocity speed. And they have way to actually model the velocity speed of their instrument as it falls through the water column, which is not trivial in itself because you're trying not to go too fast. Yeah.
The picture gives the impression that it's always attached to the crane there by the wire.
Ah, sorry, it's not.
Okay,
It's
dropped.
released. That's why it's difficult to know a priori control its falling speed. They don't want to because the ship otherwise is moving with surface gravity waves. You would take your instrument, move it up and down. Instead, you want to profile uniformly and as steadily as possible. And so it's detached. It goes all the way to the ocean bottom. At some point before hitting the bottom, mostly, there is a ballast that gets dropped and the instrument comes back to the surface. It has hit the bottom a number of times because topography measurements are not as accurate everywhere as you might wish. So the instrument gives you this fast response transmitter, gives you the theta prime, and then there is a more accurate but slow response transmitter that you can use to measure instead the background temperature gradient. Now, this very quickly, I don't want to go into much detail, but just to understand what actually needs to be done. You're not even done. I mean, you've already heard people complaining about the number of assumptions, but there are more that come at every step. And just to understand that it's not easy. Now you measure your chi. The background temperature gradient is something you can measure quite accurately. That's something we feel very confident. But the chi is the part that is delicate, because you have to measure the variance, or the temperature fluctuation, down all the way down to the scale of actual molecular dissipation, which we said scale with the Bachelor scale of order of 1/3 of a centimeter or so. So what you do here is that you're plotting chi, so this is the temperature gradient spectrum, as a function of frequency, because the profiler is actually following as a function of time. You can then conversion frequency to a spatial scale by multiplying by the speed at which the instrument is falling. But what they're showing you is this particular line is one particular spectrum that they measure. It's the spectrum of chi, and it shows you that first it's growing and then it starts decaying rapidly downward. It decays downward because finally here is where molecular processes are taking away the variance. This is a place where turbulence was pretty high, so there was a lot of variance. You were generating a lot of fluctuations. Instead, the continuous line is a fit to this spectrum, which is a Bachelor spectrum. In this particular case, there are a number of spectra that you can try to fit in. Just to show you that you want to make sure that you measure most of the variance under chi. Right? Now you see that if I look at the jagged line, it comes down here, and then all the lines collapse and start growing up. This is the instrument noise. At some point, you can measure things smaller than a certain threshold value. So in this case, you can see that the area under this curve has dropped substantially down. So probably the area under the curve has been measured. Whatever was missing is a bit irrelevant to the total value of chi. But on top of it, what people like to do is that they fit a spectrum, so they can extrapolate where the spectrum would go. By the time you measure where turbulent processes are coming, the spectrum is essentially rolling off as the minus k squared. You can actually fit it out, and so you extend the integral. But so that works very well when you have a lot of variance in the system. You're in a place that is very turbulent. There are a lot of gravity waves that break all the time. If you go in a place where there is very little variance being generated, now this is your curve, and you see that they try, and then you hit your noise level going up here, and you see that they try to fit this empirical spectrum. It's not clear that you can really say much. So when variance is small, the instrument is not going to be accurate enough to compute the whole variance, because you are moving the noise level starts overcoming the signal. Yeah? Yes?
When you said one of the challenges of directly measuring the buoyancy was that it's hard to keep the measurements at the same location. So did it do any better when you measured temperature?
So in this case, that's not a problem, because if you remember in the formula, the chi, this is a temperature gradient squared. So I just take the temperature gradient at whatever point it is, and then I square it. So it's a correlation of a value with itself. So that's much easier because I measure it once and I just square it. And this is the background gradient, but that's a ratio. I'm not computing the correlation between these two. So I eliminated the necessity of measuring two different quantities at the same point. Maybe I should have said it. That's why a variance budget is a much more straightforward approach, because now I don't have to compute any more correlations.
My question is that given the difficulty in measuring the low variance situations and the ease to measure the high variance situations, shouldn't we worry that maybe the net measurements are biased towards the high ones?
I'm not so sure I would say that they're biased towards the high ones, but there is clearly a threshold in chi below which you shouldn't trust the measurements. So we're never going, with this particular approach, we are never going to measure turbulence diffusivity. Well, we get to diffusivity, but turbulent flux is below a certain threshold, because once it goes below a certain value, you can't really do it. That's why we're going to review 3 different methods, and it's the intercomparison of the 3 that gives you some confidence that the approximation you made are probably sensible. And it also tells you if you go below or in region of 2-week turbulence, at some point some of these methods start being not consistent, and tells you that probably the noise levels are becoming an issue. But I would agree that how low is low turbulence is something we don't really know, because at some point it will go in places like what you were showing, the mid at mid-depth in the water column below the wind-driven circulation and before you get really into the abyss, the numbers typically turn out to be smaller than they can be detected. So we just know what is an upper bound, but the values might be much smaller than what they have been measured. Yeah.
Can you say again what's the rationale for the fit, the spectrum?
Okay, so I didn't say that's really a bachelor spectrum. You know that if you assume that you are at scale below the Kolmogorov scale but larger than the bachelor scale, there is something called the bachelor spectrum, which is just the constant variance flux through the system. So it's a k to the -2 spectrum, but since for temperature, but I'm looking at temperature gradient, so it becomes a k to the +1, and then has a roll-off that is due to the diffusion that gives you the -k² slope. That said, then there is Krajina that has a slightly different version of the spectrum. There are many different versions also. When you are going to read the literature, everybody seems to prefer a different fit. So you just hope that you measure enough of this inertial range all the way down to here so that you compute the most of the area underneath here, and that extrapolation doesn't matter. If that extrapolation really matters, you're not on particularly solid grounds to claim that you know the spectrum. It's based on k. This is frequency because the instrument is falling down. Then they take the frequency and multiply by you divide by a velocity, and you get a wave number. So that's why they have to measure the velocity, and they know the velocity because they measure the pressure, and they see more or less at what speed they are falling down because that's their depth. And they had to devise an instrument that has the right profile to mostly fall vertically and at a very steady speed, because otherwise, if you start moving up, you can. Your probe is going to be affected by noise even more than in these profiles. And that's why this instrument is so accurate, is that its falling speed is so precise that they can push their noise level much further down than most other instruments that have been devised ever since that are cheaper, but they're not going to be so accurate. Is everybody sufficiently worried at this point about how you measure diffusivity or buoyancy fluxes through a variance budget? And remember that you have to be in a place where you're guaranteed that temperature dominates the buoyancy fluxes. In the ocean, unfortunately, in a lot of places there is salinity and you can't avoid it. So this formula was due to Osborne and Cox, and they mostly use in the upper thermocline early on to actually measure turbulent fluxes and start getting some sense to what extent approaches like this work. We'll see that that approach is not being used as much today because it can fail in a number of ways, mostly because of salinity contamination. But we'll use it and compare it with the other ones. A second way you can do a budget, which, as I said, is the one that is most commonly used, but I want to introduce the temperature variance budget because overall I feel more confident about that one than I feel about this one, because you'll see what happens. Now, what you do is that you go through the same kind of argument that we've done before, but now for the temperature, for the variance of kinetic energy. So you write your U bar equation, you subtract it from the U equation, so you get an equation for the U prime fluctuation, the dt of U prime. Then you multiply by U prime and you take an average of that, so you get an equation that again has the rate of change of turbulent kinetic energy, advection of the turbulent kinetic energy, diffusion of the turbulent kinetic energy by viscous processes, pressure work, and now these are all inside a divergent term, and then instead on the right hand side you're going to have turbulent fluxes acting against mean gradients in the shear, mean gradients in the velocity. Now you have a W prime B prime that appears when you multiply your buoyancy equation, your vertical momentum equation that has a B on the right hand side, and you multiply it by W, so you get a W prime B prime. This is the conversion between kinetic and potential energy. It's the fact that indeed every time you mix, as we said, you are transferring W prime. If it is a stably stratified system, you're advecting upward negative buoyancy perturbation, so it's typically a negative definite term. You're converting in a mixing process some of the kinetic energy into potential energy. You generate potential energy, and then you have the dissipation of turbulent kinetic energy by viscous processes, and nu is constant. Averaging is for the moment still sub-inertial. Yes, the question was whether the averaging is still sub-inertial. So it's the same averaging as we've done before. And then at the next step, however, we are also going to assume that we take an average, not just on, we first average on sub-inertial time scale and then on a large enough patch And we'll see what we mean by a large enough patch, because we'll see practical example where we do it. But a large enough patch that we can assume that the turbulence over that patch is stationary and it's not advected in or out of that domain necessarily. So over that domain there is no divergence out or into the domain. So the balance is between these three terms. This is again a generation of, can be a generation of variance. It will typically be, because you remember you had a velocity shear in that simple movie that I showed you at the beginning of a Kelman-Helmholtz instability. So they were just a linear shear to start with, and as soon as the instability develops, instead you have all these turbulent fluctuation that have clearly generated more variance in the turbulent kinetic energy. So this is the turbulent velocity, or the turbulent stress, or the eddy stress acting on the mean gradient, or the mean shear. But now you also have a buoyancy flux, and then we also have to represent what is this viscous dissipation of kinetic energy in a case where the turbulence is isotropic. It turns out that this term is equal to 15 over 2 nu, the vertical gradient. Again, we can only measure vertical gradients of the horizontal velocity in some directions. The 15 over 2 comes about because if you assume isotropy, then you have to be smart enough and remember what is the relationship between u prime squared, v prime squared, and w prime squared. And there are relationships that I'm happy to discuss afterwards. It's not particularly important, but in an isotropic field, if it is divergenceless, there are special relationships that give you a 15 over 2 and not just 9 times, as you might expect. The gradients are not all the same in all directions because of constraints due to incompressibility. So now, once we've written this equation, we can assume again the vertical gradients in the shear dominate, as we've done before they typically do, and it's the horizontal velocity that dominates. So we get to this equation that is essentially the same as before, but just horizontal advection acting against the shear in the horizontal velocity. But we're still pretty far from having something we can easily deal with, because with an instrument, we can probably measure the mean shear. We can measure the fluctuation in the vertical gradients of u, because we're going to see how we measure small velocity fluctuation in the vertical, but we still have these two big terms that are not so easy to relate. This is the one we want to measure, but there is this whole thing that is also appearing in the budget that we don't know quite to measure. You remember that I said that the last thing we want to start having to do is to measure correlation of variables. That's very hard, and now that is appearing in this equation. So this is work done by Osborne in 1981, and you're going to enjoy it, because the thing he said is that, well, okay, now I'm going to define a flux Richardson number as the ratio of this term to that term. This is what I've written here. So now, indeed, my equation, because I introduced this flux Richardson number, can be rewritten so that the buoyancy flux is equal to this a combination of this flux Richardson number times the dissipation of thermal variance, right? Just that the flux Richardson number is this ratio. I didn't really do anything. I'm just hiding the ignorance in this flux Richardson number. Then I do a second step that apparently helps a lot. I define the flux Richardson number divided by 1 minus the flux Richardson number, and I call it gamma. Now it seems simpler. Now I related the buoyancy flux to gamma times epsilon, and epsilon is by definition the dissipation of thermal variance, so it is 15 over 2 dz of u prime square. Okay, so now the problem is that I relate the buoyancy flux to something I can measure epsilon, and something that seems to be even more complicated than epsilon, because it's the ratio of the buoyancy flux to the turbulent generation of variance that I cannot measure. So Osborne, at the time, I think, quoted the paper by Ellison of people that had looked at how much buoyancy flux you typically generate through shear instability. And the argument there was that indeed, as in the experiment I've shown you before, you had some mean shear, that is the energy source that drove that instability, because the other energy source, I mean, there was a stable stratification, there wasn't really much energy to extract from there. It's stable, it's not unstably stratified. And what they were showing is that as you generate all this turbulence, so as this system starts working, so you extract energy from your mean shear to generate the turbulence, and as a result you also mix buoyancy, because that system is mixing across buoyancy, right? It's increasing the mean potential energy of the system. You started with the system was stably stratified. If you mix it completely, you move the barycenter of that system up, right? If it was stably stratified, the barycenter had to be on the lower side of the half point, but when it's perfectly mixed, it moved up. So every time you have a shear instability, you tend to increase the potential energy of the system. Yeah. No, you cannot talk yet. Yeah, I think it's on.
Could you please elaborate on the second assumption that the del u bar is equal to del z of u h bar?
This one, I'm just again
Yeah.
assuming that vertical gradients dominate and it's horizontal velocity that dominates over vertical velocity. So out of that whole gradient, it's really the vertical gradient of the horizontal velocity in the ocean that tend to dominate in subinertial timescales.
Okay.
It's the aspect ratio of motion is pretty flat.
All right, thanks.
Yep.
I'm not sure if I understood correctly. So at the beginning of your talk, in the range of frequencies, there was F and then N, and then after N, you called after N more turbulence.
Yeah,
now
it's more nonlinear.
Yeah. Now, even anything after F is turbulence in
This definition.
and they're also isotropic. So the region between N and F.
I don't know how isotropic they are, but it turns out that the gradients that dominate are on scales smaller than n. That's where you tend to find most of this variance. If you remember, we looked at those plots, the energy was still increasing, and most of that gradient is really dominated by where that spectrum peaks. And generally, that's a frequency smaller than n.
Also, that for internal waves, the correlation between B prime and W prime is 0. So it's not the kind of flux.
Absolutely. They should be in quadrature. That is a property of the linear waves. You can't a priori say that that's the reason why you don't have to worry about what happens here. But consistently, you can say if this relation, well, I don't know, can you really say that this relationship has to hold scale by scale? I don't know, because you would have to claim that since internal waves don't contribute to this, they also don't contribute to that. Yeah. But in practice, you really see from the shape of the spectrum, they really pick the scale of the order of the Bachelor scale, or in this case the Kolmogorov scale, because we are looking at momentum. So most of the contribution is the scales that have frequency typically larger than n.
This relationship for W prime B prime equals 0 for internal waves is only true for waves that are neither growing nor decaying, just like any other waves. But
Yeah.
but that's always true. I mean, that's the same with baroclic instability. When they're neutral waves, they don't have any fluxes. So you have to look at the waves that are either growing or decaying to get some.
No,
some
I think all he's
fluxes
saying is
out.
dB prime dt plus n squared W prime is equal to 0, so W prime and B prime are in quadrature always.
No, I
So I
suspect
take
that
a
if
time
I
average.
suspect, well, evidently, I suspect that TRE's waves that while they grow or decay actually have a non-zero W prime.
But we are averaging over a long enough time that if it's just a transient growing and decaying, it doesn't have any effect. We want persistent effect. Instead, turbulence is always going to drive a buoyancy flux, a negative buoyancy flux consistent, because it's always mixing, it never unmixes. While waves sometimes will grow and sometimes will decay, and that is ignoring all this variance or the divergence or the stationary assumptions. Indeed, if you look on shorter time scale, things will grow or decay. So what about gamma? There is a sense, sorry? Yeah. So now we said that we expect that some fraction of the kinetic energy that was extracted by the turbulence goes into potential energy. That much we know. Mixing will tend to do that. But it's not clear that we know what that fraction is. And if you don't know anything about the number, then you make it up and say, well, what about it is 0. I guess the first paper quoted as 0.25. So, well, we'll assume that it's 0.25. I want just a second to explain how we measure at least the shear, then we get back to this 0.25 and what it is and what it isn't, and especially how much does it matter what it is. To measure the shear, what is being done, it's again, you use the same instruments. Apart from having a thermistor, a fast response thermistor at the top of your instrument, you also put a shear probe. This is a piezoelectric element that when it gets deflected generates a current. And since it's falling down through a horizontal current, it gets deflected, and you can reconstruct the lateral variation in the shear. So it's effective at measuring this du dz prime squared. And again, you have to do something similar. If you measure, this is now your epsilon, is the spectrum as a function of frequency. These lines are the measured spectrum that again hits a noise level, so it goes from some low frequency to high frequency, and then at some point you don't have any signal. Here you don't even have a model spectrum for typical turbulence, so people made one up. I think it's interesting that the spectrum is typically used to fit this data and see whether they are consistent with the expectation. Comes from, I think the name is Nasmyth, that published in his PhD thesis, never been published in any published literature, but people always compare to that empirical spectrum. But again, if you have high turbulence levels, so this is an experiment where the epsilon was very high, so then you see that you're measuring most of this variance. The spectrum is reasonably well captured. This is what, 2 orders of magnitude below the value it was up there, so that you can just chop off the noise and you measure most of the area under that curve, which is your full epsilon. Again, as Paula was worried about, when instead the variance levels are very small, well, look at this spectrum here. You are essentially hitting the noise level straight away, so you can't really say you are below the threshold of sensitivity of the instrument, so small turbulence levels are going to be an issue. But coming back to this gamma, so what can you do? Well, at least oceanographers are sensible people, and they decided, well, we have now 2 independent ways to measure the W prime B prime. One was based on this Osborne-Cox formula, which is related to the chi, the dissipation of thermal variance, and we have a second method that is based on measuring the dissipation of turbulent kinetic energy, which depends on this gamma we don't know, but supposedly the buoyancy flux is the same, because if I'm measuring it at the same place, in a place where thermal temperature dominates buoyancy fluxes, then I can just equate these 2 expressions. This is what I'm writing here, and then I can solve for gamma. Right? So now gamma is the ratio chi over epsilon, which I can both measure, the temperature stratification, which I can measure. So I could try to do a number of experiments, see whether at least the gamma, how much does the gamma vary. If the gamma varies all over the place, then I'm in no man's land, because the second approach is not really useful. If that gamma doesn't vary too much, and we had to say how much is too much, then maybe there is a hope that the gamma parameter, even though I don't know where it comes from, and there are people, including here in the room we heard yesterday, working on what sets that value, but if it doesn't vary too much, it might not matter dramatically. So here I'm showing a whole bunch of experiments that have been done since the original work by Oki, that try really to get deep into this argument, in the 80s. I'm crossing out a few cases because they were not associated with turbulence generated by gravity wave braking. They were in coastal areas where there were other processes like solid borers and hydraulic jumps, so you don't expect necessarily that gamma to be the same. And if you look at the numbers, I mean, you can spend time in looking at the various estimate, but in the end, the number indeed doesn't vary too much. I mean, it's typically within the range of 0.1 to 0.3. I would contend. You find some cases where it's a bit smaller, maybe in some cases it's a bit larger, but that's the typical range. Now, I would contend that a factor of 3 variations there is absolutely acceptable, because we are going to worry only about changes in buoyancy fluxes by at least an order of magnitude. Those are the ones that really matter from the large-scale perspective. Variation factor of 3 are within the noise of anything we're talking about. So, knowing the mixing efficiency beyond this range is probably not going to be terribly useful, because those variations are small enough that it's going to be very hard to make sense of what they would imply on large-scale circulation. We want to see variation of orders of magnitude, and gamma doesn't seem to change by orders of magnitude, which it could. You remember that there was gamma is flux Richardson number divided 1 minus a flux Richardson number. It could go all the way to infinity for all we know, but it doesn't. And I think that is quite important, because these are typical oceanographic conditions in places where you have strong turbulence or weaker turbulence. And this is, I would contend, the real rationale for oceanographers to decide that the number should be in that range. And it stops here, because you'll hear, and we'll go a bit deeper in, I don't know, do we have time? We are going pretty slow. We'll go a bit deeper in a few minutes, hopefully, into statements where people claim that it's by comparing the different approaches that we really estimate a gamma and convinced ourselves that this is 0.2. We'll see that that's actually factually not true. This is the only way gamma has been estimated, and this is the rationale for being within that range. If you find it compelling, great. If you don't, that's all there is. Yeah.
Did you say why you crossed out some values in the
Yes, so these were experiments done in coastal region where the mixing was not associated with gravity wave braking, so you're really entering in a different regime. It's not typical of open ocean condition, which is what I'm focusing about for the most part today.
Thank you.
Which also confirms that mixing efficiency can be very different from whatever happens in that range. If you go in different physics from what is gravity wave breaking. Now, maybe just the last point, Paula has already mentioned it. In this particular example, the vertical buoyancy flux can be also expressed. We know that it's always negative and the stratification is always positive. What it tells us is the buoyancy flux can be related to minus kappa t dzb. It has to be a negative definite term. The bdz is always positive, so we can use what is called a diffusive closure, because the flux is always acting to reduce the vertical gradient. I'm putting again the feature. The figure, you start with a very strong gradient across this interface, light water over dense, and as a result of mixing, you reduce this gradient, so the buoyancy flux is acting against the mean gradient. So if I make that kind of closure, I can just now express this relation that we got for the buoyancy flux, so how you measure the buoyancy flux, as estimate of the turbulent diffusivity itself. Just that you find a lot of time in the literature people publishing value of turbulent diffusivity versus buoyancy fluxes. From the physics point of view, the buoyancy flux is the more fundamental quantity, but I can introduce a turbulent diffusivity. For example, if I have the Osborne-Cox, this is the Osborne-Cox formula for W prime B prime. Well, if I just divide by the BdZ and I put a minus in front, I get an estimate for kappa t. T is now for turbulent, and I put a chi here to remember its estimate based on an estimate of chi. I can do the same from the Osborne formula, where now the buoyancy flux is just minus gamma epsilon, and therefore kappa t turbulent, based on epsilon measurement, is just gamma times epsilon over the stratification. Yeah.
Is there an issue with the filtering procedure, and how do you define the vertical gradient of buoyancy? Because in that particular case, there is a steep gradient in the buoyancy profile, and at the end, there is a very smooth gradient. So
yeah, but the gradient is still going in this direction, just that it's uniform. Then I have a step in the gradient, and the buoyancy flux has reduced that gradient. I could have chosen a better picture, but I was trying to be consistent with the only picture I've shown, a better estimate. The problem that I think you're truly alluding to is that here I don't have an obvious scale separation. It would be nicer to have a uniform gradient and then the turbulence on small scale. So in that case, you have a scale separation, and what we said before is a bit more consistent. And in the ocean, typically, that's the situation. You have large-scale gradients through the water column and a turbulent patch acting on them. You don't find very often very sharp transition in the middle of the water column. Yeah. Why do you expect to have?
Why do you expect to have a different value of kappa t based on two different estimates?
I really hope not.
Yeah, right.
But I'm using two different estimates, and I want to remind what I actually measure. I hope that they converge, but if they don't, it raises a question whether I measure them correctly.
Okay.
Absolutely. I hope they are the same thing. But if you're not a theoretician, you realize that there are a lot of approximations made before, so you're not fully confident that they turn out to be the same. Okay, we'll go very quickly through this one, otherwise we won't see any of the observational experiment where actually we validate some of these ideas have been validated. The last method in which that you can use to measure the turbulent diffusivity is now very different from the first two and relies on putting a tracer in the water column and then seeing how it spreads through the water column. Of course, if I put a tracer, the first thing you'll see is that there are very strong geostrophic motion that will steer the tracer laterally. And this is a picture, I think it's from Eckhart, where you see the tracer. Is that Velander? Okay. I stolen it from Bill Young's notes for the GFD summer school, but I didn't write who he stole it from. So you see that you form all these streaks along a density surface for the most part in the ocean interior. But at the same time, there are these gravity wave breaking that constantly try to mix a bit of the tracer across density surface in the other direction. So if I look over time, the tracer will spread across density surface as a result of that mixing. Right, so now again, I can write my tracer equation. Now this is a passive tracer. And my tracer equation, average over a subinertial time scale, is affected by the turbulent fluxes of the tracer fluctuations. The Reynolds flux is here. And again, if I use a down gradient closure, I get a turbulent diffusivity times grad C bar. Now this is isotropic in mixing in all possible direction. It's whatever the turbulent diffusivity is. So you see that the tracer itself, on average, is being mixed across density surface by these turbulent processes. Now, I think that I'll just state it. I won't go through any of the details that I was planning to, otherwise we really don't get anywhere here. But believe me that you can now write, and I'm trying to keep the problem simple, but you can write moments of the tracer now, ZC, vertical moment. So I take C, I multiply by the vertical position of the tracer, the Z, the vertical position in the water column, and I take an average of the full volume. That's the first moment of the tracer, or if you want, is the barycenter, or the center of mass, or where the tracer is in the water column. Right? I can also introduce zeta 2, which is the center second moment. Now I see, if I know what is the barycenter, or the center of mass of the tracer, I can look how much it spreads compared to the center of mass. Because we said that that's what supposedly is being increased as diffusion is acting. The tracer starts very confined over a density surface, and over time it spreads around that density surface. Here the point was that if we make a number of really drastic assumptions, let's assume that the isopycnals are flat. We don't need to make that assumption. We could work in density coordinates and avoid it. We're not going to do it here. But if I assume the density coordinates are flat, and I'm assuming that the steering velocity u is horizontal, there is no vertical velocity in this problem, just so that I don't have a drift of the center of mass, which I can include if I want to, but to keep it simple. So now, and I also assume that kappa t is independent of z. That instead is an approximation that essentially needs to be made to make progress with this method. And generally, that's not a terrible assumption, because I put the tracer very well confined in the water column. So on the scale over which the tracer is, kappa t doesn't vary very dramatically. So, but I cannot use it if I allow the tracer to spread too much in the vertical. But if I make all these assumptions, since there is no vertical velocity, the first moment of the tracer, the barycenter of the tracer, remains always at the same place, because there is no mean velocity moving it up and down. But the second moment of the tracer instead will spread in the vertical, and it spreads at a rate which is given by kappa t times c over c. This is the turbulent diffusivity. If the turbulent diffusivity was absolutely constant, horizontal in addition to the vertical, this would be just 2 times kappa t. This is a formula due to G.I. Taylor. So just that the rate of growth of that second moment increases the turbulent diffusivity in the water column. If there are variations in the horizontal, then there is this correlation. But what is important now, you have a completely independent way of measuring the turbulent diffusivity by just looking how the tracer spreads across density surfaces. Of course, it sounds very easy in theory. In practice, it's Jim Ledwell and Woodsall. They had to find a tracer that you can measure quite accurately in the ocean for very long times, because these processes are very slow. So he needed a tracer that he can measure over years, which he managed to. It's a sulfur hexafluoride, and it's very stable in the water column, and you can measure it over years. The drawback is that once you put that tracer in an ocean basin, you cannot go back to that same ocean basin for 20 years or so, because it's polluted by the tracer you put the previous time, and you keep seeing it. So it's already been done in the North Atlantic, it's been done in the Southern Ocean. I think the Pacific is still mostly clean, because there was only a coastal experiment. So now we have these 3 methods: a variance budget, a turbulent kinetic energy budget, and a tracer method. And we are going to look at the first seminal experiment that tried to compare the 3 approaches, because up to that point there were serious questions about whether all this approximation of homogeneity and isotropy were sensible for estimating ocean mixing. So until the tracer arrived in play, that was based on a completely different approach. People were quite skeptical, or at least worried, that some of the approximation might seriously break down and not be robust enough to get useful estimate of this turbulent diffusivity of the buoyancy flux that we care about. So the first experiment that was done by the group in Woodsall, the Microstructure group, this fluctuation on small scale are often called microstructure perturbations, was the North Atlantic tracer release experiment. It's in the North Atlantic off the coast of Africa. We are in the middle of subtropical gyre. It's a pretty quiet region in the ocean, and most importantly, it's a region that is on a flat abyssal plane. There is no topography underneath. They wanted to make sure that they didn't have all the complication that Bill talked about on Monday of gravity, local gravity wave generation, or anything made it special. They really wanted a boring place, because it was the first time they wanted to measure turbulent diffusivity with 3 independent methods. They injected a tracer at 300 meters below the surface. They are pretty close to the surface. That was easier to do. And at that point, they didn't care about measuring mixing in general. They just wanted a place where they could compare the different estimates. So the tracer was injected at some point here. This, I think, it's a measurement that was done a couple of weeks later. So you start seeing the tracer is being spread around. A ship went and sampled all these profiles to reconstruct the tracer, and this was 6 months later or a bit longer. You see these 2 big stripes of tracer as being stirred around laterally. At the same time as they were measuring the tracer, they were taking vertical profile with the HRP over this whole region. You see a cluster of values here. This is center over where they injected the tracer. So they are taking a lot of vertical profiles of both chi, epsilon, and the vertical gradients of buoyancy and temperature. So now they have all the independent estimates of kappa, and they can start comparing them. Of course, the tracer is going to give them only at one depth, while the other estimates give you the profile over the full water column. So if you took the tracer estimates, we said that what they had to do was compute the second moment. So this is zeta 2, the second moment of the tracer compared to the density surface where it was injected. So they see at what rate is growing in time. They actually compute the second moment 2 weeks after injection, then 6 months and a bit later. And then they fit a line through this point to say how fast does it actually spread through the water column. They had to measure the dz2 dt. So this is zeta 2 as a function of time in days, and this is the fit through their points. And the value they got was something of the order 1 plus or minus 0.2 times 10 to the minus 5 meters squared per second.
So it's not really a check, but it is diffusive.
It's not a check. Well,
I mean,
they contend it looks very linear.
Yeah.
Right. So if it is linear, the diffusivity is constant over the time, and so maybe it is truly diffusive. Oh, fair enough. Yes, they do. Well, you worry also about that, whether you're seeing a diffusive process or just the central limit theorem working for you. But yes, that works. Okay.
So in many turbulent flow, for instance, Richardson first experiments, you don't expect to have a diffusive.
It's in the vertical, cross-isopic. In the horizontal, typically you don't, but in the vertical, you have the scale separation. The waves don't break at very large scale, so at some point you average over the largest scale already. And yes, something I'm not showing here, you can look at the profile of tracer concentration C as a function of depth, and they looked as Gaussian as this. This is C as a function of C. Remarkably so, yeah. At least over the first 6 months, and that's why I stopped at 6 months. At later times, they started noticing that the whole Gaussian was sinking through density space, but they think it had to do with the particle SF6 sticking to particles in the water column and therefore becoming not neutrally buoyant.
So I would have thrown out the first point at short time.
Yeah, you can, but it's zero compared to anything after that.
But then that, I can't believe that's the line that you've drawn. If you toss out the first point and just fit through the remaining points, it will have a very different slope, won't it?
What do you mean? It has, well...
actually, it doesn't have to go
to zero. It doesn't have to go to zero.
It
is whatever is the initial thickness. They contend that actually this is the release. Because 2 weeks after, it starts already looking pretty Gaussian. And yes, they didn't measure at the moment they were injecting because they don't want to profile while they inject. Otherwise, they start smearing the tracer straight away.
Yeah. Okay.
10 days is just too short? I mean, that's what it is, right? 10 days, isn't it?
It's 2 weeks. It takes 2 weeks. They actually start, I think, a week after the injection, and it takes 2 weeks to do that whole sampling. So
I guess what bothers me, it's really 3 points, and if I pick and I can pick the last 2 points, which you'd think would be the most reliable because the tracer is spread over the greatest distance, then I would fit a line with a much steeper slope.
Okay, so the other thing they have done, except for this problem of a bit of sinking, is that they also have measurements 1 year later and 2 years later, and the diffusivity gets a bit smaller, but you're talking about 20% change. I mean, not very large changes, so they can do a fit on longer time scales. They were a bit concerned about using that, at least it's not in the original publication of Ledwell et al., because as I said, there was some net sinking of their particles because they seem to be not neutrally buoyant, so they were worried that if there was any kappa T vertical variation, then whether they didn't know whether they were aliasing the estimate because they were sampling a different part of the water column or because diffusivity was truly different. But I wouldn't worry too much. I mean, okay. This is what was published. Now, we're going to try to be more confident by using the other 2 estimates that we have, and I'm going to show in detail the kappa T based on epsilon. This is the epsilon, the turbulent kinetic energy dissipation that you see has values at 300 meters where the injected tracer of order of, did I cut the curve? No, here it is, 10 to the minus 9 watts per kilogram. that's the number that Bill told us is typical in the ocean. But then you see that by the time you get to the bottom, it's already 10 to the minus 10. So typical is always relative to where you're looking at. This kinetic energy dissipation change by orders of magnitude all over the place, and it's actually decreasing towards the bottom quite consistently. So if you believe that your buoyancy flux is just gamma, some constant that varies within factors of 3 times epsilon, that would imply that the buoyancy flux is decreasing towards the ocean bottom here. Now they can also estimate finally the diffusivity. If you remember, Osborn formula was that you take epsilon divided by the stratification, and you have to multiply by a gamma, and this is what they get here. The first remarkable thing is this kappa t is much more constant than this epsilon, which changes by an order of magnitude. It's close to 10 to the minus 5 throughout the whole water column. Interestingly enough, well, maybe let me say, they multiply this number by a gamma that they call 0.25, and they get that the result is their estimate of kappa t is 1.2 plus or minus 0.2 10 to the minus 5 meters squared per second, which they contend is consistent with this value here, which it is. But what I never realized, it was for this lecture I went carefully, they use 0.25 and not 0.2, even though that was the number that was typically used. And as a result, they contend that this was proof that 0.25 is the number that you need for the mixing efficiency. And ever since they went back to 0.2 because it was working better in other conditions. So you see that, but worse than that, then you'll find a lot of places in the literature where people contend that the Natri experiment is what convinced people that gamma equals 0.2 is the number that has to be used, because it showed that by using that there is consistency. So people are very willing to move that number up and down in a bit. I don't think there is any measurement in the ocean that necessarily constrain it more than that range they gave you before. The different experiments have used different values without worrying too much about how close or how far it should be from that 0.2. You can do the same with chi, an estimate of chi, and you get again a number which is of order 1 times 10 to the minus 5 meters squared per second. So all three methods at least seem to give consistent values, order of 10 to the minus 5 meters squared per second, which, if you remember, it's an order of magnitude smaller than what Monk had estimated was required to maintain the abyssal ocean stratification, or that buoyancy flux, or the net upwelling that we see occurring through the global ocean. But we are measuring at 300 meters, and you remember Walter Monk was talking about anything happening below 1,000 meters. At the beginning, this was still a surprise, because the understanding, and actually the evidence, is that the internal gravity wave field is more energetic close to the ocean surface than at the bottom, for the most part, and so they were expecting, if anything, to get larger turbulent diffusivities. But, of course, you have to worry about the fact that there are also gradients in the turbulent diffusivity at the denominator. If those are much larger, they might overcome the rate of variance generation. In any case, at that time, when these measurements were made, people were quite surprised on how slow the turbulent diffusivity was, and it seems, at least it suggested, or was casting some doubts on the argument of Walter Monk, because the number didn't seem to match up with the acknowledgement that they were measuring different parts of the water column.
So the fact that on one side you have a passive tracer, and on the other side the tracer are not passive, is it a problem in principle, or,
well,
or should you expect?
Not if the turbulence is mixing, I mean, if the turbulence process is mixing all tracer equally. Right? You assume, which is the zeroth law of turbulence. Yeah. So this seems a vindication again in that sense. Yeah, the buoyancy is not special from that point of view. Once you mix everything at the same rate. Kappa t should be only depending on kinematic quantities, the velocity itself, not on the tracer. But it's always an open question. The classical counterexample is potential vorticity, which, for example, seems to mix in different ways than the passive tracer, because it has constraint on the constraint on the velocity
there will
field.
be correlation, strong correlation.
Yes.
I'm not sure to understand what do you mean by the zeroth law of turbulence for this problem, because you could still have dissipation that does not depend of diffusivity and still a re-stratification of buoyancy.
Re-stratification?
Yes, making the difference between a passive tracer and buoyancy.
Well, if it re-stratifies, however, it will also prevent the tracer itself from being diffused in the vertical, right?
There could be a balance between both.
Yeah, I find that for this problem, I would worry much more whether the tracer is truly passive. That's always a fair question, because it's not easy to just tag a water parcel. But as long as you tag a water parcel, probably doesn't matter too much. I mean, gravity wave breaking is a pretty dramatic event that tends to mix everything. I doubt that you're going to get strong feedbacks from the buoyancy itself that acts differently on buoyancy than on a tracer. But I don't know, there might be experts in the room that know more.
Can you offer an example where a tracer mixes differently than buoyancy? Can you give us an example of a flow that you consider fairly turbulent where it does it?
But not buoyancy.
But potential vorticity is
it's just the potential vorticity has a strong
2D,
constraint
almost
on
2D,
you.
and we, according to Bill, it doesn't satisfy the zero load turbulence.
So the profile of epsilon, that's many profiles averaged together, right? So that's
Sorry, I should have said, yeah, and they are only averaging here on the set of profiles close to where the tracer was released.
okay.
But you have an order of 50.
What does it look like if you take a single profile? I mean, would it be like one flight through the atmosphere?
It's very noisy.
Well, how much turbulence is there? Is there just one location that's turbulent for one realization? I mean, how intermittent is the actual process?
It is quite intermittent, but you're going to have a number of events on every single profile. So not the full water column is turbulent any time, but there are always places that are turbulent. That's what you tend to see. So it's definitely an intermittent system. So did you average long enough to get reliable and stable statistics? Again, they try to contend that is the consistency of this measurement that would suggest that probably yes. This is one of few cases where you had of order of, I mean, the whole set had 10 by 10 vertical profiles. You've seen all those dot points. So you have order of 100 profiles plus another 25 in the center. Probably in this case, you had enough statistics to do it quite reliably, but it's the only example that we have in the literature. Well, there are another couple that we're going to see, but typically you don't. So you're taking a risk on that too.
Well, it's not just for estimating that number. It's interesting, but on its own right, how turbulent is actually a snapshot of a column of water, right?
It's a log normal distribution, so there are very rare events that are very large. That is actually a very important question in terms of how you average these epsilons. We could get into that because arithmetic averages are probably not a good idea for a log normal distribution, so people try to worry about it.
Just a quick question. So do the values agree well with what we see in complex models, like the oceanic models?
Oceanic models don't resolve any of this, so they just generally prescribe a kappa. So
okay.
There is no the agreement. Well, we'll see. They pick the kappa that they like. Paola talked a lot about the 10 to the minus 5, but Walter Mank was insisting on 10 to the minus 4, so also there the oceanographic community is a bit idiosyncratic in which numbers they decide are most relevant. But that's next time we'll explain where the variations matter and what should be done, at least.
Okay, so I'm wondering why they choose this boring region to measure this kappa. Like you say, this boring region in the Atlantic?
Because it was likely to be sufficiently homogeneous that they could repeat all this measurement and get stable statistics. If you are in a place where there are very strong variations laterally, then it becomes a bit more difficult to sample a large region and assume that the homogeneity and isotropy assumption really hold.
But then the fact that you have like another magnitude lower value that you expect from the Munch, would be a signature that it's actually this kappa T is highly non-homogeneous. You can have some
absolutely, absolutely. That's why they got program managers to pay for a second experiment straight after this. Now they said, well, the point here was they said, we can do it, we can measure the turbulence, now we're going to measure it in an interesting place. But it's much harder. So the error bar goes up, right? You want to be in the place where the error bar can be kept as low as possible into this intercomparison. It was the first time they really did a tracer release experiment on a large scale. They weren't sure that they could actually track this tracer for that long and be there reliable. So they wanted to put the tracer close to the surface. There were a number of limitations that they wanted to make sure that they could address. We'll skip this one except to say that it turns out that if you are close to the surface in this natrey region, indeed, the buoyancy is dominated by temperature. But as soon as you move below, so, and these two curves, this is chi, and this is how much variance is generated through buoyancy. The two curves are on top of each other. It's a vindication of the Osborne model, but as Osborne-Cox model. As soon as you move below, salinity contamination becomes very important, so you can't quite use it. And just to show that typically, and this is a place where you would expect that to happen, there is water that flows out of the Mediterranean into the Atlantic at around 1,000 meters, and so that's where you start having all this salinity contamination. So typically, oceanographers don't use very often the Osborne-Cox approach, because salinity contamination can become quite important and make the approach quite unreliable. That's why, for example, even in that paper, as I've shown you the profile based for epsilon and for kappa T based on epsilon, but not on chi, because they don't report the values on chi, because they show at the end that it's consistent, but they weren't sure that it would be consistent throughout the water column. So very quickly, this is important because we needed to start next lecture. Now we go to an interesting place, the Brazil Basin. It's the same group of people. It's the Microstructure group of Woodsall. It's Jim Ledden, Ray Schmidt, John Toole, Kurt Polzin. They go now to a very deep basin of Brazil. They want to have a region now that is partly pretty smooth in terms of topography, but partly pretty rough, because you go on the mid-Atlantic ridge. They are going to inject the tracer at 4,000 meters depth. Now they want to see what happens close to the bottom, because this is a time when a lot of things conspire to give the impression that topography was probably important in generating gravity waves, and gravity waves probably did tend to break close to topography. We heard Bill talking mostly about the work from the altimeter and the evidence that the barotropic tide was losing a lot of energy into the internal tide around rough topographic features like the mid-Atlantic ridge. Here they go from the opposite side. They say, well, if there is a lot of internal gravity waves generated locally, maybe there is a lot of turbulence. Maybe the kappa T is large in those places and not up in the water column. So they release a tracer at this point here. It's a number of streaks. 1, 2, 3, 4. They generally have an injector. They put the streaks there. This is where the tracer is injected as a function of depth and longitude. It's this place here. Then the tracer starts spreading out over time. And you remember that if I look at the spreading of the tracer compared, this is how the density surface in the ocean, the white line, and the color is the contour of the tracer. I think a year later, you see that it starts spreading across density surfaces as it moves around. It moves a bit to the left and a bit to the right of the injection place. At the same time, they collect around all these dots, and there are many more in here. They measure vertical profile again with the HRP, so they can make again their estimate of the turbulent diffusivity and the buoyancy flux through the whole water column. Here I'm plotting just the epsilon profile for a few regions along this latitude. These are average over a bunch of profiles, and this is the topographic section. And you see that the epsilon is increasing towards the ocean bottom consistently. That's very different from what we've seen before, where epsilon was decreasing towards the ocean bottom. The profile I'm showing here are all in this region where we are over rough topographic features. If they went to the left, where the topography was much smoother, they got a picture much more consistent with Natri, where epsilon was decreasing towards the ocean bottom. If you believe that gamma doesn't vary too much, the turbulent kinetic energy dissipation is just proportional to the buoyancy flux. What that is telling you is the buoyancy flux is increasing rapidly towards the ocean bottom. Doesn't look like as dramatic, but you see that this is a logarithmic scale. This increases by 1 or 2 order of magnitudes toward the ocean bottom. It's a dramatic increase of buoyancy flux every time you get close to the bottom topography. Again, Bill will be as unhappy about these estimates as the previous one. They only use 2 points. This is the injection after 2 weeks of the tracer, and this is 1 year later. They take the difference between those two values. So they assume that it's diffusing. They don't verify that it's diffusing. It looks very Gaussian. The profile looks very Gaussian. That's their only defense, I guess. So they take 1/2 times the second moment. Now you look, this is how Gaussian the profile looks. The black dots are the accurate estimates, and the dotted line is a Gaussian fit to it to measure the second moment in Z. If they take 1/2 time the rate of change of the second moment over 1 year, they get something that is for the diffusivity, which is of the order between 3 and 8, 10 to the minus 4 meters squared per second. So now the number is much larger. It's as large as what Walter Bank was talking about, if not larger. They can do the same thing with the epsilon profiler, by going at the same depth as the tracer, and I get a value which is between 1 and 3, 10 to the minus 4 meters squared per second, so it's still the same order of magnitude. It's definitely much larger. Here is 0.2. You can talk with Kurt Paulson about the history of that. I don't know, they never even apologize for changing the number, but they just do it. Now, since they have vertical profiles of kappa T, they can you have a vertical profile through the whole section that goes from Brazil over the mid-Atlantic ridge. They can plot kappa T through the whole water column to start giving you a sense of what is a map of that turbulent diffusivity. And this is a paper. This must be one of the papers coming straight after Gent and McQuillan in terms of Moss-Seidel and physical oceanography, because it's become a pretty seminal picture. Because what it shows you now is kappa T as a function of depth. Now that you've seen that the approach seems to work, they were bold enough to try to make their full map, so there are vertical profiles everywhere you have points, and you see that the color scale is a bit funny. This is in term, the units are 10 to the minus 4 meters squared per second, 1 monk. So most of the this part of the water column, the value is 10% of that value, so it's 10 to the minus 5 meters squared per second. So it looks like this is a bit like the natric condition, where like the diffusivity is not changing all that much. You're on pretty smooth topography here. This is the continental slope and shelf. It's very old crust, it's pretty smooth. It doesn't generate probably internal waves. There isn't much turbulence. Actually, if I look at the buoyancy flux, which is this kappa T multiplied by the stratification, we know the stratification increases towards the ocean surface, so the buoyancy flux increases towards the ocean surface. But when I go over this region, the mid-Atlantic ridge, this is new crust, this is very rough, a bit like what you see out of the window here, but underwater. So the topography is incredibly irregular. Now the kappa T is still small if you go very high in the water column. At the 300 meters where they did the natric experiment, it will still be small. But now as you move towards the bottom topography, the value increases toward order 1 and up to 10 times larger, 10 to the minus 4 meters squared per second. There is a very consistent pattern with turbulent diffusivity increasing towards the ocean bottom. Turbulence is much more active at the bottom of the ocean than it is towards the surface. This was quite important because it starts suggesting that indeed it's consistent with this picture that if it is gravity wave breaking, you see that the turbulent diffusivity expands quite a bit above the topography itself, a few 100-meter folding scale up to 1,000 meters. So there is turbulence that is associated with gravity wave breakings that probably are radiated away from this bottom topography. You might expect that to be the case because there is a lot of irregularity. So any mean flows flowing on this side would tend to generate a very rich wave field, and especially small-scale wave fields that are more likely to be nonlinear and interact compared to what happens on the left-hand side of the picture, where it's much smoother and you probably generate less waves. So the important thing here is that we see the kappa T is increasing towards the ocean bottom and the buoyancy flux is increasing towards the ocean bottom. And now I'm going to conclude skipping all of these other things, but I want to leave you with a conundrum, which is what we're going to discuss next. So now what we learned is that what observations seem to suggest, and I've shown you only one example, now there are plenty more that have been taken in different parts of the ocean basin, is that when you have strong mixing, the strong mixing in the ocean water column tends to be larger towards the bottom topography. It tends to be strong where there is rough topography, and it tends to be enhanced toward the ocean bottom. What I mean by mixing here is the buoyancy flux increasing toward the ocean bottom, and if you want, the turbulent diffusivity is increasing towards the ocean bottom. So now think about a water parcel in the middle of the water column. So this could be a water parcel over the mid-Atlantic ridge. Now this water parcel is apparently being mixed a tiny bit with waters above it, which are lighter, but much more with waters below it, which are heavier, because we said the kappa T keeps increasing towards the ocean bottom. But if I mixed more with denser water than with lighter water, I tend to get denser as a result of mixing. But if I'm denser, then I'll start sinking. Now that's a problem because Walter Munk told us that he argued that mixing is what brings all waters from the abyssal ocean back towards the surface. And because of the profiles of mixing that have been collected starting from the 19s, it looks like mixing is doing quite the opposite, making water denser and make it sink towards the ocean bottom. We also know the mass is conserved, the water has somehow to come back to the surface. So the question you can think about until my next lecture, which is Friday, I think, is how does the water come back up? Because mixing, according to the profile that we have identified, is not going to do it. And I'll stop here.
Thank you. So if you don't mind, can we begin the next lecture with some question about this? I'm sure there are many questions.
Absolutely.
So, okay, because the only strict constraint we have is this one.
Food.